Welcome back to the Deep Dive. Today, we are soaring right past the conceptual stage and into the absolute engineering grit it takes to make urban air mobility, or UAM, a real tangible thing.
Hmm.
We're not talking about those optimistic timelines you see in the news. We're talking about the hard constraints that define whether this is commercially viable at all.
Right.
And in the world of UAM, that whole commercial model, it really rests on two pillars. They're totally non-negotiable, rapid turnaround on the ground, and absolute 100% safety in the air.
And that's exactly the tension point, isn't it? For any of these air taxi services to actually make economic sense to compete with a car, the aircraft has to have a high sortie frequency.
Meaning it's flying constantly.
Constantly. It has to be charged, checked, and ready to go again almost immediately after it lands. But that speed, that utilization, can never, ever compromise the safety standards of commercial aviation.
And today, we've got a rare look behind that curtain. We're looking at a detailed engineering specification for the energy storage system, the ESS, for a really fascinating vehicle, the P13 series parallel hybrid eVTOL. So this is a true deep dive into the blueprint. This isn't just, how do we stick a big battery in a drone? This is about the core power philosophy. We're taking the perspective of a top-tier aerospace architect.
A very methodical approach.
Exactly. Our mission today is to use that rigorous aerospace methodology, top-down MECE principles, to really unpack how engineers design a battery system that has to be both a powerhouse for vertical lift and, at the same time, a certified life-saving safety device.
And that architectural approach is it's essential. To even start, you have to really get the strategic implication of this P13 hybrid architecture. In a pure electric vehicle, a car, the battery is everything. It's the whole energy reservoir.
That's the fuel tank.
The P13 system is different. It's a series parallel hybrid, so it couples the high energy density of fuel through a thermal propulsion unit, or TPU, basically a generator, with the ultra high power density of the batteries, the ESS.
So that coupling, that fundamentally changes the battery's job.
Completely. The ESS is no longer the single energy source.
Okay.
This is the critical shift. For the P13, the ESS transitions away from being the fuel tank and instead takes on two really dynamic roles. First, it's a power buffer, handling all the extreme peaks in demand.
Like takeoff.
Exactly. And second, and this is the most critical part for certification, it is the safety redundancy source.
So that dictates everything.
It dictates the entire design. We are prioritizing power density, the ability to dump current fast over sheer energy density. But, and this is the key, it still has to have enough energy stored to fly a 40-kilometer mission and have, by law, 5 minutes of guaranteed reserve power for emergencies.
Okay, let's unpack this. Because that shift power for safety and peaks, but still needing energy, that creates these immediate, fundamental conflicts for the engineers. It forces them into a set of almost contradictory constraints.
It really does.
When you lay out the P13 spec, the very first thing you see is this diagram they call the impossible triangle. And it really is the perfect name for it. It's this set of constraints that the ESS designers just have to solve.
It's called impossible because if you optimize for any one of those points, you inherently compromise the other two. The physics are just brutal.
How so?
Well, let's say you try to maximize energy density, how far it can fly. To do that, you usually have to accept a higher internal resistance in the cell, which then throttles your power output, your C rate.
So you get range, but you can't get off the ground.
And what's more, those high energy chemistries are often less stable, which makes your safety margin shrink, and getting it certified becomes, exponentially harder. So you end up with this great battery for a road trip, but it can't deliver the punch for a vertical takeoff, or it's just too volatile to ever get certified.
Okay. Or you could go the other way.
Exactly. Or you design for pure maximum power, a massive surge of current. But to do that, you need heavier internal structures, more cooling, and all that weight and bulk just eats into the space you need for energy capacity.
So the whole exercise isn't about maxing out one thing. It's about finding that sweet spot in the middle.
That mathematically optimized, certifiable sweet spot. That's the whole game.
So let's define the three vertices of this impossible triangle from the spec. Vertex 1.
Vertex 1 is extreme power, pulse discharge. This is the VTOL requirement. Vertical lift is just the single most power-hungry part of the flight. So the ESS needs a sustained immediate discharge of more than 10 C.
And 10 C means 10 times the pack's nominal capacity in current.
Right. And the spec is really specific. 7 C to 10 C for 30 seconds or more. That massive instant current draw It defines everything, the chemistry, the cooling, all of it.
Okay, vertex 2 is high energy density. This is the reminder that, we still need some gas in the tank.
That's right. Even as a power buffer, it can't be all flash. The spec demands a system-level density greater than 200 watt-hours per kilogram.
At the pack level.
At the pack level. And that's what makes sure you can fly that 40-kilometer mission, handle a detour, and critically, have the energy you need for an OEI-1 engine inoperative landing. If your density drops, your payload suffers, and the whole air taxi model just falls apart.
And the third vertex, the one that governs everything, is absolute safety.
This is the hard ceiling. The catastrophic failure probability has to meet the EAS's SC VTOL enhanced category goal. Less than 10 to the minus 9 per flight hour.
1 in a billion.
One chance in a billion hours of flight. You can't stress how demanding that number is. To get to 10 to the minus 9, you can't just prevent failure. You have to assume it will happen, and you have to manage and contain it.
So the solution philosophy isn't about cheating physics. It's about managing risk down to that billion to 1 number.
Exactly. The core principle in these documents is systematic engineering trade-offs. It's multidimensional optimization. We're designing for failure.
Meaning
We have to ensure that redundancy, isolation, and thermal containment are built in from the molecular level of the cell all the way up to the aircraft structure. If a component fails, and it will eventually, the system has to not just survive but stay operational so the pilot can continue a safe flight and landing.
Okay, so let's shift from constraints to function, following that top-down MEC approach. The ESS isn't just a passive box of batteries.
Not at all. Think of it as the airframe's care system, from racing, but just elevated to aviation safety standards. It's a high-speed energy valve, constantly deciding in milliseconds whether to push energy out for a hover or pull it in from the generator.
So let's nail down these 5 core functions. The MECE breakdown.
Okay, first, and this is the one that really defines the hardware, is peak power assist, or power shaving. Like we said, VTOL is the most demanding phase, so the ESS provides that instant 10C pulse, coupling its output with the generator's continuous power.
That's fascinating. So the battery lets the combustion engine be smaller and lighter than it would need to be otherwise.
Precisely. It optimizes the whole propulsion chain. Second function is the absolute bedrock of airworthiness, emergency reserve. The OEI support.
The life-saving power chain.
That's it. If the thermal propulsion unit fails catastrophically, the engine quits, the ESS has to instantly provide reliable, sustained power to get the aircraft down safely. It's the guaranteed last-ditch power source.
Okay. Function 3 is about efficiency, energy recovery, and buffer. Regeneration.
Right. The P3 motors that provide thrust can also act like generators when you descend or brake. The ESS has to be able to absorb that sudden high-rate energy without overheating. And during cruise, if the generator is making surplus power, the ESS just tops itself up in air charging.
It makes the whole system more efficient.
Much more. Okay, fourth function speaks directly to whether people will even accept these things flying over their cities. Acoustic management. Silent operation.
Ah, the noise issue.
Huge issue. You can't have a combustion engine running when you're taxiing or landing near a hospital or a residential building. So the ESS has to deliver enough power for pure electric operation in those noise-sensitive zones. Without that, the business model just collapses.
And finally, function 5, which is more subtle but just as critical, system voltage stabilization.
Right. The ESS acts as a high-frequency buffer on the 800-volt DC bus. Why? Because a sudden 10C power demand can cause a massive voltage ripple or spikes and dips.
Which could damage the electronics.
It could fry the flight controls. The ESS dampens all of that out, ensuring you have clean, stable power for the whole aircraft. It's the power quality manager.
So that mandate, being a safety-critical, high-powered dispatch core, it leads to one key architectural demand: no single point of failure. Which brings us to the physical structure.
It's the driving imperative. The spec calls for an 800V distributed redundant architecture. Nominally 800 volts, but the operational range is wide, from 600 up to 900. But the real key is the topology.
So tell us about that. How do you make it redundant?
The ESS can't be one big block. It has to be made of multiple, say, 6 or more physically and electrically independent battery packs. It's called a split bus architecture.
So instead of one big fuel tank, we have 6 smaller, independent tanks.
Exactly. And the power electronics for each one, the controllers, the contactors, are also isolated. This architecture means that if one pack has a thermal event or a short, it doesn't spread electrically or thermally to the others. It's the only way to meet that fail operational requirement.
So the pilot can still land the aircraft.
Even after a catastrophic component failure, the failure becomes a localized, containable event, not an airframe catastrophe.
Okay, we've established the strategic role, the high-level function. And now, here's where it gets really interesting.
Yeah.
How do you translate that complex mission into cold, hard, measurable numbers? The KPIs.
It's a process of reverse engineering the mission. You model every second of flight to figure out the absolute harshest metrics you need to hit. These are quantitative targets.
So let's walk through them, starting with energy.
The requirement is clear. System-level density must be greater than 200 watt-hours per kilogram at the pack level.
Which isn't the headline 300-plus number you hear about for cars.
No, and you have to remember why. This 200-watt keytree has to be achieved while delivering 10C power and maintaining that 10 to the minus 9 safety factor. That means you're adding heavy, non-flammable containment structures, redundant electronics. All of that adds weight and brings the effective density down.
Okay, then there's the power requirement, the real signature of this system.
The signature metric is the pulse discharge, greater than 10C, sustained for 30 seconds. And that duration is critical. It's just long enough to transition from vertical lift to forward flight or do an extended hover. After that, for an emergency, the continuous OEI power has to be sustained at 5C or more.
Why is that difference so telling? 10C for lift, 5C for an emergency descent.
It tells you exactly how the aircraft is using its energy. The 10C burst is violent. It's fighting gravity. The 5C continuous power for OEI, though, that's just managing a controlled descent. You're not trying to lift the aircraft again. It tells you the cells have to be optimized for peak current delivery, not endurance.
And since it's a hybrid, it has to be able to suck energy back in just as fast.
Absolutely. The spec calls for a 3C to 5C charging rate. That's crucial for two things: absorbing regen energy efficiently, and more importantly, for rapid in-air replenishment from the generator during cruise. If you can top up fast, the battery is always ready for the next high-power event.
Now let's talk about the economic KPI, life cycle. Honestly, 2,000 cycles at a sustained 10C discharge. That sounds almost physically impossible with today's chemistry.
That's an excellent point, and it gets to the heart of the trade-off. It's not easy. The trick isn't in the cell chemistry alone, but in the operational envelope management. The BMS will enforce a strict upper and lower limit on the state of charge. You might only operate between, say, 20% and 80% SOC. By limiting the depth of discharge, you protect the cell structure and massively extend its life compared to a car battery that you run from 100 down to 0. The BMS acts like a custodian for the cycle life.
And finally, the foundational electrical spec, nominal 800 V DC.
The high voltage is a critical choice, and it's all about weight reduction. We aim for 800V in a 600 to 900V range. Why not 400V? Well, you double the voltage, you have the current for the same power.
And that matters because of heat loss, I squared R.
Exactly. Heat loss is proportional to current squared. So if you have the current, your heat loss drops by a factor of 4. Less heat means you can use smaller, thinner copper wires.
So you can literally see the weight savings.
Yeah. Moving from 400V to 800V lets you reduce the cross-section of the entire high-voltage wire harness by about 45%. Imagine the main cable shrinking from the thickness of your thumb to a pencil. That one decision saves dozens of kilograms. It's huge for payload and range.
So to meet this brutal combination of requirements, you have to get into the chemical core. We're talking specialized aviation-grade cells now.
The material choices are where these trade-offs are physically made. For the cathode, the spec calls for high-nickel NMC chemistries, NMC 811. That high-nickel content pushes the energy density.
And on the anode side?
To get past the limits of graphite, the spec mandates silicon-carbon composite anodes. Silicon can absorb way more lithium than graphite, but the problem is it swells like 300%.
Wow.
So you have to meticulously manage that expansion with sophisticated internal structures so the cell doesn't just fracture under stress.
The spec is also very specific about using high-power cylindrical cells. Why that format?
Cylindrical cells, like the 21700, are preferred for aerospace because they're just inherently more mechanically robust. Each cell has its own strong, rigid metal can. That structure is just better at handling the severe G-loads and the specific vibration profiles of an aircraft.
And you mentioned a big technological leap on the safety side, semi-solid electrolytes.
This is a preventative measure that buys you critical time. By reducing the amount of flammable liquid electrolyte, The chemistry itself becomes more stable. It elevates the thermal runaway trigger temperature. A normal EV cell might go off around 150 Celsius. The goal here is to push that to over 200 degrees Celsius.
And that 50-degree margin.
That 50-degree margin gives the BMS precious extra seconds, maybe 30, maybe 60, to detect a problem and isolate the pack before it's too late.
That margin is essential, because achieving that 10 to the -9 target means you have to assume failure will happen. It's a philosophy of designing for failure.
Absolutely. You start with that fail operational principle, the split bus topology we talked about.
Oh.
If a single pack have a thermal event, high-speed contactors have to isolate that entire channel instantly.
Now let's get into a problem that's unique to aviation, the high-altitude problem.
Ah, yes. Paschen's law. It's fundamental physics. The voltage needed to cause a spark to jump across an air gap is related to the air pressure. As you climb, the pressure drops.
Less air means less insulation.
Exactly. The air turns into a leaky sieve. An air gap that's perfectly safe at sea level can suddenly become a high-risk arcsing path at 25,000 feet.
So how do you mitigate that?
Extreme conservatism. The spec mandates that the creepage and clearance distances, the shortest paths for electricity along a surface or through the air, have to be increased by 3 to 4 times the sea level standard.
Wow.
You also use specialized, non-conductive materials to reinforce the insulation and prevent partial discharge, which is the electrical stress that happens right before a full arc.
Okay, now for the most violent safety requirement, the battle against thermal runaway. The sources cite a peak temperature of 805.7 degrees Celsius.
That's the temperature of the plasma in a ejecta cloud. It's hotter than molten lava, and the cell housing has to contain it. The non-negotiable goal, mandated by DO 311A, is no propagation.
One cell goes, but it stops there.
It must be halted at that cell wall. It cannot spread.
So how do you do that? Let's break down the containment strategies: prevention, detection, and containment.
First is early detection. The BMS has to alert the system within 1 second. We're looking for precursors. Long before the peak heat, a failing cell starts off gassing, releasing flammable gases at temperatures as low as 185 Celsius.
So you look for the gas.
You use sensitive gas sensors, yes, but you combine that with that's active management or directed venting. The housing has to have dedicated, structurally sound venting channels to direct those high-temperature toxic gases safely away from the cabin, the cockpit, and any critical flight surfaces.
Before we move on, what about the electrical safety features for the maintenance crew?
Absolutely vital. The high-voltage interlock loop, or HVIL, think of it as a physical tripwire in all the connectors. If a technician even starts to unplug a high-voltage connector, the loop breaks, and it sends an immediate non-digital signal to open the main contactors. Power is cut in milliseconds.
And insulation monitoring.
That continuously checks the resistance between the high-voltage lines and the aircraft chassis. If the insulation degrades and that resistance drops, it alerts the crew to a dangerous leakage risk long before it can lead to an arc or a shock.
So if the hardware is the armor, the battery management system, the BMS is the brain, the digital nerve center.
That's right. And the certification level proves it. The software and hardware have to meet design assurance level A or B. DALA is the highest safety level there is. Same as the fly-by-wire flight controls.
A failure cannot lead to a catastrophe.
It must be shown to have zero probability of leading to a catastrophe. It's an incredible standard to meet.
And the BMS's primary job is high-fidelity state of X estimation. Let's start with state of charge, SOC. Why does that need DALA certification?
Because the accuracy is critical. It has to be accurate to within plus or minus 3% over the entire life of the battery. To get that, you need sophisticated algorithms like extended Kalman filters.
And if it's wrong?
If it's wrong, if it overestimates the energy by more than 3%, a pilot might commit to a landing thinking they have their 5 minutes of reserve power when in reality they don't. It's the equivalent of running out of fuel at the worst possible moment.
Then there's state of power, SOP. That's a predictive function.
It's arguably the most complex calculation. It has to accurately predict the maximum safe power you can pull out or put in for the next 120 seconds.
Why 120 seconds?
That's the calculated time a pilot needs to assess an emergency, decide to go around, or commit to a landing. The SOP has to be reliable enough to tell the flight computer, yes, you can initiate a 10C go-around right now, with 1 in a billion confidence.
And state of health, SOH, feeds into all of this.
SOH is the real-time tracking of battery aging, and that data is vital because it shifts the entire maintenance paradigm from reactive to predictive. You can see a module is approaching its retirement threshold weeks in advance.
And to make sure this digital nerve center itself doesn't fail, it also has to be redundant.
Absolutely. The architecture uses dissimilar redundancy. That means using chips or even software from two different manufacturers, so a bug in one system won't take down the other.
A common mode failure.
Exactly. And for critical sensors voltage, temp you use triple modular redundancy. 3 sensors measure the same thing, and the system uses a voting mechanism to find the true value, instantly ignoring a failed sensor.
Okay, beyond safety, we go back to commercial viability, which hinges on ultra-fast charging.
The business model collapses if the turnaround is slow.
Yeah.
The engineering goal is fierce. Charge to 80% SOC in 15 to 20 minutes.
That's up to 400 kilowatts of power. Pushing that much current in generates a massive amount of heat.
A huge thermal challenge. So the spec mandates that the onboard liquid cooling system must be fully active and at peak performance through the entire charge cycle. If the temperature gets too high, you get lithium plating, which permanently degrades the cells and invalidates that 2000 cycle life goal.
So the cooling loop is part of the mission-critical charging infrastructure.
It has to be.
Okay, we've covered power, brains, safety. Now, the physical body. The ESS isn't just cargo bolted to the floor. The spec treats it as a core structural component.
It's a design necessity for weight optimization. The battery pack is often structurally integrated, acting as a load-bearing member. That means the pack housing itself has to meet airframe standards like DO-160G.
What are the key structural requirements for that housing?
The primary one is crashworthiness. The pack has to withstand a severe impact, say a 20-gram forward crash load, without breaking or intruding into the passenger cabin.
And the spec is astonishingly precise, demanding deformation be controlled to less than 10.423 millimeters.
Right.
Why that specific number?
That number is the absolute maximum allowable displacement before the pack risks compromising the occupant's survival space, specifically their footwell. The pack has to deform safely outward, not inward.
And there's also fire resistance.
Yes, the housing has to act as a shield against external fire. It has to meet ISO 2685, which means withstanding an 1100 degrees Celsius flame for 15 minutes without penetration.
And finally, vibration resistance.
VTOLs have complex vibration profiles from the rotors and motors. The pack has to survive that for thousands of hours without anything loosening or cracking. A microfracture in a connection could lead to a short circuit.
So all this theory has to be proven in the validation gauntlet, the tests for certification. Let's talk about the most dramatic destructive tests.
These are pass-fail, no excuses tests. First, thermal runaway containment. We intentionally trigger a single cell failure.
And what are the success criteria?
It's absolute. The failure must not propagate, and, critically, no external flames or solid fragments can escape the housing. If one ember gets out, the design fails. Period.
It's like in simulating a crash. The 50-foot drop test.
This simulates a severe hard landing. The criteria here are all about post-impact survivability. The pack can't break open, and there can be no fire, no explosion, and no toxic chemical leakage for a full 15 minutes.
The rescue window.
That's the mandated window for first responders to arrive and start extraction.
And what about electrical fault testing?
The external short circuit test. You intentionally short the system with extremely low resistance. The system has to safely and instantly break the circuit with its fuses or contactors, preventing a fire.
And finally, testing against Passion's law.
The altitude low pressure test. The pack goes in a vacuum chamber to simulate 25,000 feet. You verify that the increased insulation distances work and that the seals hold.
And the journey to these final tests uses the V-model verification process. You start in the virtual world.
Right, with MILSIL, model, or software in the loop. You verify the math of every BMS algorithm in a pure simulation, running millions of scenarios before you ever write the final code.
Then you integrate real hardware.
That's HIL, hardware in the loop. You connect the actual BMS controller to a real-time flight simulator and run failure injections. You simulate a sensor failing or a contactor burning out, and you verify that the system responds correctly.
And the culmination of all the ground testing?
The Ironbird. This is a one-to-one physical setup with the real ESS, the real motors, the generator, the cooling loops, all integrated. You run thousands of endurance cycles, simulating every possible flight scenario to prove it all works together.
Only after all that do you finally go to the destructive tests.
The aerospace architect leaves nothing to chance.
From an operator's perspective, the ESS is the single highest cost, most limited life part. So the engineering has to look past certification to the economics of a 10-year operation plan.
Lifecycle management is profitability. The first key strategy is modular design. The spec demands the ESS be engineered for a rapid battery module swap in the field.
So you don't ground the whole aircraft.
Exactly. You minimize aircraft on ground time. Swapping a module should take hours, not days. The second strategy is predictive maintenance.
Using that SOH data from the BMS.
Right. You couple that with AI algorithms that analyze fleet data, and you can schedule a module replacement weeks before it actually fails during a planned downtime.
And finally, what happens when a module is retired from flight duty at 80% SOH?
Second life application. These batteries are still incredibly valuable. They transition into stationary energy storage, often buffering power for the charging stations at the vertiports themselves. You maximize the asset's total economic value.
So what does this all mean? We've looked at the 5 stringent pillars of success for this P13 ESS.
It's a masterclass in compromise and systematic safety. It's defined by 1. Extreme power, the 10C boost. 2. Fail operational safety, meeting 10 to the minus 9. 3. Absolute thermal containment. 4. Mission readiness with the DAL, ABMS, and fast charge. And 5. Structural integrity.
It's harmonizing race car power with commercial aircraft safety.
It is, and it's the non-negotiable baseline needed to build the public trust for UAM to even exist.
And the horizon is already changing. What's next? What breaks the current design ceiling?
The next generation is already in testing. Solid-state batteries are the main focus. They're expected to hit 350 watt-hours per kilogram by 2026-2027. More energy, and they're inherently safer without the liquid electrolyte.
That would completely redefine the energy vertex of the triangle.
It would. We're also seeing AI-enhanced BMS, using machine learning to predict cell failures weeks ahead of time. And for longer-range missions beyond the P13's urban scope, hydrogen hybridization is being developed.
We talked so much about how engineers ensure the failure of one cell doesn't spread, and how the BMS software is this DAL digital guardian. But what if that software itself failed? Not a sensor, but a subtle, common mode software bug that took out all the digital safeguards at once. What's the final, non-digital, hardware-based guardian against a full system catastrophe?
Well, that final guardian has to be independent of the software. It's the circuit breakers, the fuses, and that hardwired high-voltage interlock loop.
Exactly. The lesson here, what really defines aerospace safety, is that even with the most sophisticated DAL of the software imaginable, the ultimate safety of the airframe still relies on a simple, physical break in the circuit. It proves that crucial difference between digital safeguards and absolute physical containment barriers.
You always have to have that ultimate physical fail-safe. When everything else fails, the architecture has to guarantee the current just stops flowing.
That is a phenomenal walkthrough. Thank you for showing us how that impossible triangle is systematically engineered into reality.
My pleasure.
And thank you for joining us for this deep dive. We'll see you next time.